So in this lecture, we discuss on some Borel sets and some something on integration, like integration as a measure. So this is slightly diverted topic. So one thing is discuss on Borel set, and another the other aspect is on integration. So so discuss on Borel set first. So what is Borel set? We know the collection of our Borel set is a Borel sigma algebra. So any element of the Borel sigma algebra is Borel set. But what are the Borel sets? So Borel sets are, we know this half open, half closed. These are Borel. So these are Borel. And these are Borel. So A to B, these are Borel. And these are Borel. So can we find, is that all three type of set needed? That's the question. So the answer is obviously no. You can construct one set from the other using complementation and union, and obviously by intersection, because intersection is also in the sigma algebra, because you can write the intersection if a1 a2 an and dot 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 is in the Borel sigma algebra, they are Borel set, then we know this complement is there, so and their union is there, so complement and their union, so that must be in Borel. But this is by De Morgan's law. This is just intersection dot dot and then complement. So you take the complement again. So if you take the complement of that, so you will find this is the this is in this the intersection in this Borel sigma algebra. So intersection are in the Borel set. So now how do you construct from say this type of set to infinite interval? That is easy. You just so if you want to say construct this set, so this is just nothing but say minus n to a. So from n equal to 1 to infinity. So this minus n to a finite half open half closed interval, the union is this. So similarly, if you take a to n, the union n equal to 1 to infinity, that is actually a to infinity. So from this set you can easily find the infinite thing, and obviously from the infinite thing you can find the finite thing. That is also easy, because a to b is just nothing but minus infinity to b intersection minus infinity to a complement. So similarly the other one, that is the complement of this minus infinity to a. So that means we can construct the remaining two from the anyone. Now what are other set we can construct? Now we can construct this type of set also, a to b. So how do you find the open interval, construct open interval AB using that closed interval, half open, half closed interval? So that is this like that. So you will take this and take the union overall n equal to 1 to infinity. And it is easy to check that these two are equal. These two union, the right hand side union and the left hand side open interval are equal. Similarly, you can construct that open using open to the close. That also you can easily construct. So you can find that this is nothing but the intersection of all type of set A plus B plus n 1 by n. So this is the n equal to 1 to infinity intersection. So now we can easily construct also this type of set using this half open half close. Like this is nothing but a minus 1 by n, a minus 1 by n to b, and union overall n equal to 1 to infinity. Similarly, you can find you can construct the open interval using closed interval, or if you start with anything, if you start with any set of all closed interval, you can construct the set of all half open, half closed, all half closed, all closed, or all open interval. Even if you start with the all open interval, you can construct the half open, half closed, and closed intervals, infinite intervals. All intervals you can construct. So all the intervals are are Borel sigma in Borel sigma. So all intervals are Borel set. Next, is the singleton set is Borel? Yes, the singleton set is Borel set, because this you can write in like that: a minus 1 by n, a closed, and this take intersection over n equal to 1 to infinity. That is just the singleton A. We can easily prove that. I will show one proof, and the other will be rest will be homework. So this we can construct any finite set. So any finite set and any countable set is so. Therefore, any countable sets is Borel set. So because it is a countable set, a countable union of the singleton set. So that's why Q and Q complement, which is set of all irrational numbers, are countable, are Borel. So I'll see only one thing. I'll prove this one, and the rest will be proof of this. So why these two are equal? You have to show that A in right hand side, but no other element in the right hand. So obviously A is in the right hand side. A is in A minus, so A is there, so because A is closed. So for all n. So therefore A belongs to the intersection. So this is okay. Now why this no other elements are there? So why this intersection is only A? So that is also easy, because if you take B, which is strictly greater than A, then B does not belong to the set for any n, for all n. So it can't be belongs to the intersection. Now question, if you take B which is strictly less than A, is that B belongs to that set? If B is strictly less than A, then what happens? Then so here is A, here it is a B, and here it is a minus 1 by n. So if you take if you choose such a n, that choose n such that B is less than a minus 1 by n, then what happens? Then that B not belongs to the set a minus 1 by n, A closed, outside the set. Therefore B cannot be in the intersection, since it is not in a single element. Say choose M, say M. So it can't be, since it is for M, it is not belongs to the set, it can't be in the intersection, because if it is to belongs to the some intersection, B must belongs to the every set. So but since B does not belongs to a single set, actually for all n greater than M, B cannot be belongs to that, because once n is greater than M, then it will be again is close to A. But can we choose such a element? Question: can there exist? Is there exist such a n M such that question is there? So can always there M such as this? So if I choose A and B very close, can M exist? But yes, M exists, because this is equivalent to say that M is actually less than. Sorry, it is right. B A minus B. So here B is less than A. We choose B is less than A. So this is positive. So since this is positive, it's equivalent to say that M is actually greater than 1 by A minus B. So since A minus B is positive, you can take a integer which is greater than 1 by A minus B. So A may be very close. So A minus B may be very small number, but 1 by A minus B is a very large number, maybe, but that is an integer. So we can easily choose that M, choose M, like say box of 1 by a minus b plus 1. If we choose that, then it will be, it, it satisfies this condition that b does not belongs to that a minus 1 by m to a. So that is a proof for this thing, but you can easily prove for the other also, the other thing. So everything you can easily prove, this one, this one, or this one, this one, or this one, everything you can prove easily using this same trick. So this is our Borel set. So there are some sets also which is slightly complicated type of sets, so like say Cantor-like set. The Cantor-like set is some typical type of set which has a uncountable set, but still measure is 0. Cantor-like set measure is 0, but still uncountable. So if it is a countable, then the measure must be 0. Why? So what is the measure of this? So length measure, say, or anything, any if it is a continuous measure or continuous probability. If it is a discrete probability, then the finite set has a uh, positive measure, may have a positive measure. But if it is a continuous thing, probability, or it is a length thing, then measure of this single element is 0. Why? So now, okay, so there is a theorem. It's a very important theorem. Say we have a element, say x, which is greater than or equal to 0, which is cannot be negative. And if let x is greater than or equal to 0, and if x is less than delta for all delta positive, so if it is a non-negative and less than delta for all positive delta, then only choice is x equal to 0. So x equal to 0 is the only choice. There are no other positive number which can be less than the every positive number. So because x cannot be less than x. So if x is positive, so it's trivial. So proof is trivial. If x is positive, x cannot be less than x by 2. So since x is less than for every positive number, x must be 0. So this is a very trivial, very easy to say or easy to understand, but this is a very strong result, very strong information to prove something. So let's see. So how do you prove that length of a singleton set is 0? How do you prove that? In our school geometry, we learn about this, or we heard that the point has length 0. But we never see the proof. Why is the point has a length 0? We ask our teacher that why so line segment is a consist of the infinitely many points, but every point has a length 0. But how this line segment has a length? Similar question arises for the integration. So if it is integration a to b, some fx dx, we know the integration is nothing but the area under the curve. So it is area under the curve and this area. Now there is similar type of question that is this area include that line a, x equal to a, or include x equal to b, whether it is include a or exclude a, or whether b include or not. That's the question, but the answer is again same. Whatever you can include, you cannot include, the answer is same, because the area will be same. If you just exclude a or you just include a, the area will be same, because the area of a line segment is 0. Like area of a length of a point is 0, similarly area of the line segment is 0. Eventually area of the whole line is again 0. The whole real line, area of the whole real line is 0. So how do you prove that length of a singleton set is 0? So that is like that. So a is in belongs to a minus 1 by n, or maybe say delta. So for choose delta. So for any delta, for all delta positive, a belongs to a minus delta to a plus delta by 2 in this set. Or eventually you can take that also, that thing. Better you take a minus delta to a, that will be better. Same thing actually. So what is the length of this right hand side set? So sorry, this, so this is subset of this. So belongs to that, that means it is a subset of this. Now what is the length of this right hand side? So by definition, length of the right hand side is delta, a minus delta, a minus delta, which is delta. But what is the length of this? So this is a subset. Now if a is a subset of b, then so if A is subset of B, then length of A, not only length of any measure actually, any measure is less than or equal to any that measure of D. So any measure, if for any measure that if A is a subset of B, then mu of A must be less than or equal to mu of B. Why it is true? It is true. Clearly, it is true because you can write B in terms of A union B minus A. So A union B minus A. So, and this is a disjoint. So A intersection B minus A is disjoint because this is a whole universal set, and this is your B, and this is A. So this is A and this is B. So this side is B minus A, is dotted portion. So that means the intersection is empty. So that means the mu of the same proof for the probability also. So mu of A plus mu of this, because this is our disjoint. Now we know the mu of this anything is greater than or equal to 0, so this is greater than or equal to mu of A. So this is a basic idea, such that every subset has this measure always strict less than or equal to that superset. So that means your length of this set, length of this singleton set, must be less than or equal to delta. Oh, we just this theorem slightly change. If x less than or equal to delta, and then for all delta, then x must be equal to 0. So this is same. So if x is positive, then we choose delta as x by 2. Now x cannot be less than or equal to x by 2. So now since what we have the length of A set containing a singleton A is less than or equal to delta for all delta. So and from that we can conclude that since it is less than delta for all delta, that must be equal to 0 because it can't be negative. So that's why the singleton set has length 0. Similarly, you can prove that so length of a countable set is 0 if A is countable set, then length of A is 0, because countable set means it can be written in a, you can just in the list. So this dot dot dot. Now length of this set is nothing but the length of this their union, disjoint set. So this is plus plus plus, and some series, and every term of the series is 0, so it is 0. Every term of the series is 0, so it is 0. Now, so every countable set is 0, measured 0. So length is 0. So length of Q is 0. Length of rational number is 0. Length of natural number is 0. So any countable set of length is 0. Now, what is the then for uncountable set? No, uncountable set may have length infinite, may have length finite, like 1 to 0 to 1 open interval, that length is 1. So there are uncountably many points on that set. And there's some set which is uncountable still that has length 0. That is called Cantor set. There are some Cantor like set. Cantor set are such a set where says If C is Cantor set, then C is uncountable, but the length measure of C is 0. So this is called Cantor set. There are some other Cantor-like set. We're not going details on that. How Cantor set is constructed. Cantor set are actually closed set. So just just take the info as just information that there is a set which is uncountable and but length is 0. Now question is about the area. Say what are the area? Say if you have a area measure, say mu is the area measure. Mu is the area measure. Area. So it is if it is the area measure, what happens? So if it is the area measure, then again we have to first. So same thing is there. So area of disjoint union of set is the sum of the areas, and the area cannot be negative. That are there always because area is a measure. But the extra thing is how do you define the area of a rectangle? So that's we have to first define a rectangle. So we define a area of the rectangle like that. Say in R2, so it is a rectangle. This is a rectangle. A is a rectangle. So area of the rectangle, we know this is length into breadth. So if it is this coordinate is say a comma b, and this coordinate say a comma, sorry, it is first coordinate will be changed. So it is c comma b, and this is a comma say d. Second coordinate will be changed. First coordinate is same. Here, first coordinate will be same as second coordinate will be changed. So c comma d. Now a less than c and b less than d. AB may be negative, whatever, or A may be less than B, whatever. Now, what is the area of this? The idea of the area must be intuitively that D minus B into C minus A. That should be the area. Now, there is again one question arises that whether this boundary is included or not. The answer is again same. It is like a half open, half closed. You just take this left boundary and the right boundary, but not the upper and the right. You just take the left one and lower one, but not the upper and the right one. So how do you write this set? So this is nothing but a Cartesian product. So it is a Cartesian product of two intervals. It is A to C, sorry, it is A to C, the Cartesian product of A to C, Cartesian product B to D. So this is the A set. So the set of all xy in R2 such that x is in A to C, C closed, and y in B to D. So y is in B to D. So that means, okay, sorry, no, there is a mistake. We include the upper one and the right one. We are excluding the left one and the lower one. Just exclude the left part. We also exclude the end point also. This point also excluded because we are x cannot be a. This point is excluded. This point is excluded. Now again, you can just construct that this rectangle, this half open, half closed rectangle using this type of set only. The set is like that. So minus infinity to b cross c, b not b, second coordinate, first coordinate is c, cross minus infinity to that d. So d. So what is this? This interval actually like that. This is like this. This is a c comma d, and you are taking all these points here. This thing, this part, no end. Now, how do you construct this? From this, you just take first. You just take first this thing, and then take the minus of that. So that point is a, what is the point? The point is a comma d. So a comma d. So that's say this rectangle. We write this rectangle as say ACD, like that. So ACD means that infinite rectangle. So you have a ACD rectangle and then minus that AAD. That means you just take off this part. So that means you left with only this part, this thing. Now you just take the union of that. So this is actually minus, it is set minus. Now you take again the union of uh, what? No, it's no need of union. You have to take just they take again minus that part, say this part, this set, this part. You just if you take so it is what is the point? C comma D. So you just A C comma D, and that set actually will be this portion. So this is the idea. So if this measure as a is a probability measure, then we just find we define a bivariate distribution like that. So bivariate distribution like that. So f of x comma y like that. So it is probability of x less than or equal to x and y less than or equal to y. That means that probability of this part, this probability of this set, probability of x comma y belongs to this rectangle is nothing but CD is actually the FCD. Now, how can we find the probability of this, like measure or any area? You just first take FCD. That means you are taking the whole thing, and now you take the minus FAD. Now it is a number. Now it is not a set. It is a number. So you just take minus. Now you can't just put minus because then this part will be twice minus because now it is a number, not a set. If it is a set, then if something is not there, say we know for if say 1 2 3, if you take minus 2 3 4 2 3 4, that is actually set containing 1 only. So what is whether there is or not, no matter. But if it's a counting, so there are 3 elements and there minus 3 element, that is not a single element, there is a 0. So you have to just include the 4 also. So since it's a number, you have to include that thing, that AB, this portion. You have to include that thing. So plus FAB. And that will give you the probability of this rectangle. So that is the probability of x lies between A to C, C closed, and y lies between B to D, D closed. That's the idea. And that's the idea of the bivariate distribution. So like similar like univariate distribution, that is a bivariate distribution. So this fxy called the bivariate distribution, f function is called bivariate distribution function, and this bivariate distribution is this. Now this again, if for a univariate distribution, what happened for univariate distribution? So the f of x, what is for the univariate distribution? It is just probability of x less than or equal to x. Now what is the density function for continuous case? It is just derivative of that. Say small fx. Derivative of the distribution function is the density function. But in case of 2 dimension or maybe in the higher dimension, what is the density? Now is there a question of derivative is there? So but since there are 2 variables, we can't talk about the derivative. No, then we have to talk about the partial derivative of that. So we need the partial derivative thing. So we need the 2 things: a partial derivative which is the first coordinate and the partial derivative which is the second coordinate. So 2 things are there. So and this is slightly complicated thing, the 2-dimensional thing. We'll go for when we do probability in 2-dimensional case or any multivariate random variable, then we taken care of all this thing with the partial derivative thing and the directional derivative. All these several calculus on the several variable is needed, but here we just discuss on the single variable. So now we can just omit this partial derivative thing. Okay, so now the rectangle has this area or maybe any measure or any probability measure like that. So but again the question, why this a length has a line segment has a area 0? Again this question arises. So if there is a say two-dimensional thing and there is only single line, the line segment say why this area is 0. Again, that idea is same. You just enclose this area in this line segment by a small rectangle. Now you just parallel to this. Say this line is parallel, say parallel to x-axis. Now this is say length say k, and this length is L. Now again, you can choose L as a very small, like epsilon. So k and L are epsilon are both positive. You can choose that as epsilon. Why? Because this line segment has no, it's a width but not no breadth. So you can choose if this line is say here, say line is say this is the point is say y0. Now you can choose just y0 minus epsilon by 2 and y0 plus epsilon by 2. So this length is epsilon and this length is k, say. Now the area is k into epsilon, the area of this rectangle, but area of this line segment, the red line segment must be less than that. So area of this must be less than that. That line segment say L. We call it say L. We call it say L. This is L. This line L. So now again as k is fixed. Now remember k is fixed. Now since but epsilon we can choose any small epsilon. This is true for all epsilon. And since this is true for all epsilon, so this is 0. So therefore the area of this we can choose as small as epsilon. So this area is 0, less than any positive. Now next question is if you have a line, whole line, then what happens? If you have a whole line, if you have a whole real line or any say real line or any line parallel to say real or any line, why this area is 0? Now you can't take k now. So now the length is infinite. So length is infinite, the breadth is 0. So infinity into 0, we don't know whether it is finite or 0 or infinite. But we can prove that it is 0. To prove that, we have to show that we can always enclose this line using a very small area rectangle or very small area region. We can always, for every epsilon positive, we can choose a region whose area is epsilon, but with this enclose the whole line. How do you choose? Because this is infinite. So there's a tricky way to choose that. So say this is a 0 point, and we choose say first -1 to 1 rectangle, and this rectangle say height is say epsilon. Now in the next, we choose next rectangle as epsilon by 2 length from 1 to 2, and from here -2 to -1. This length is height is epsilon by 2. Again, we choose the next one is the epsilon by 4. Likewise, this dot dot dot. So what is the area of this? The union of the whole rectangles. All the rectangles are disjoint. So is the sum of this. So what is the area of the first one? First one is 2 epsilon. Second one is 2 into epsilon by 2. The two same type of thing. So next third one is 2 into epsilon by 4. So this sequence. So this sum, and this sum is actually 4 epsilon. You can easily check that it's the infinite GP, and this is the 4 epsilon. So we choose that first one maybe epsilon by 4, next one is epsilon by 8, that one is epsilon by 16, then it gets epsilon. So okay, we have a region whose area is 4 epsilon, or maybe you can choose as epsilon if you start with the epsilon by 4, and your line is a subset of that union of the rectangles, but this union area of the union of the rectangle is just 4 epsilon, or maybe you can choose as epsilon. That epsilon is for every epsilon we can do this. For every epsilon positive we can do this. Whatever the small epsilon you give me, I can always find a union of rectangles whose area is epsilon, and that cover the whole line. So that's why the length of the area of the line is less than or equal to epsilon, and that means for every epsilon it is true, so the length is 0. So this is the basic idea to prove something with one-dimensional case, which is in higher dimensional measure is 0. So not only that, any plane in 3 dimension the volume is 0. You have to properly cover this whole plane, suitable covering of with a volume, whose area volume is with a region whose volume is say less than epsilon or epsilon for every epsilon. For a fixed epsilon, we can always find a volume of epsilon which cover this plane. That we can do in a similar manner, not only for the same 3 dimension, it can be true for the any general n dimension case. So this is the basic idea to prove something is area or length or volume is 0. So now we just discuss on the Borel sets and Borel set in some special type of Borel set with a rectangle like that. Once this rectangle is 0, area is 0, or any line rectangle area volume is 0, then their circle and every planar figure will be 0, because there are, we can always for a circle disk or a disk we can always find a rectangle which covers this disk. Once the rectangle has this area 0, the disk will be at area 0. So now go move on to the integration thing. So what is the integration basically? It's in the Riemann integration thing. So we know the integration of fx dx from a to b is nothing but the area under the curve. Is area under the curve line between x equal to a and x equal to b. So this area. This area. Now same question, if we what is the area of this integration a to a fx dx? This is 0, because area of a line segment is 0. We already proved that. So whether we are include a or b, or whether we exclude a or b, that doesn't matter. So area including line x equal to a, that line segment x equal to a, this part and this part, whether you include or not, that area will be same. So forget about this question whether x is open in a or closed in a. You can choose the both open, both closed, one open or one closed, anything you can choose. So that's why the area is like a measure. So since area is a measure, the integration also a measure. So integration also a measure. So integration of this, so we'll sometimes we write this mu ab, this integration of this interval on this interval for f. We should write f also. So we should write the measure of this f function with respect to that closed interval or open interval, whatever, that's the same. You can write that's a half open, half closed also. Or okay, better to choose closed. So closed interval have some extra advantage in real analysis. So again, this is a measure. So once this is a measure, you can always write. So any Borel set, say A is a Borel set in real line. So integration over a Borel set, like it's not a like that. Not just a interval. It's like it's a union of intervals. Say this portion, then this portion, then this portion. Then what is the area under this curve? Say x. The same we know in the classical geometry. This is nothing but the area of this portion plus area of this portion plus area of this portion. So it's just a, if A is a union of say a1, a2, a dot 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 dot, it may be countable union, countable intervals. Then this area is nothing but the sum of this area of that function of ai, I equal to 1 to infinity. Now again the question of convergency, that can be easily resolved, that because this measure is non-negative, and since this is non-negative, the series always converge, or it's converge to infinity, maybe converge to infinity. If it is diverge, we call it converge to infinity, because with the area or integration we measure in the extended real number system. For improper integral, we have some integration, maybe infinite integral. So the integration is finite means is a the integration, the measure is a real number, not the infinite. So again, this is a measure. So the integration is a measure because it is area. So that union thing we can do this. Obviously, that special function f is there, and we can go to the some other integration like that Riemann-Stieltje integration. So in that case, we measure something on the say in an interval like that. Now we are going to not the area now. Now maybe some measure on this here. Maybe some measure is, say this is the curve. Say this is the f function. So this is your f function, and this is your interval. Now we do not measure the now measure this this area. We are not measuring the area now. What we are doing actually, how do you measure the area? Basically, you are measuring area like that. So you are just taking small in partition the small part. That's the Riemann integration thing. And for every part, you are taking of this slice like a rectangle. And so if it is say delta xi, you just take f of xi, you multiply delta xi, and then the sum, and then take a limit. Limit that partition, norm of the partition goes to 0. That is the idea of the Riemann integration theory. That is actually integration if this limit exists. But now we can go to the slightly deeper idea. So limit any partition tends to 0, but that we can take f of xi I equal to say on the I equal to 1 to infinity. That is also 1 to infinity, but not this your length measure. Here we're using the length in this height into length, so area. But we are taking the height, but not taking the length here. We are taking some other measure on that, on other measure, on this delta xi. There is maybe other measure on this line. See, maybe the another probability. We have this, actually this mu delta xi is not the length, is a probability of this small interval, or maybe any other measurable function, and that is called that is sometimes written as in this form a to b f d mu. So other mu measure, or you should not write mu now there, you should other say, because mu is this measure on this on the line, so it is another measure. So in our Riemann integration theory, this mu is the length measure and this m is the area measure, but it is called a Lebesgue-Stieltje integral, Riemann-Stieltje integral in the Borel set. And if you take the Lebesgue measurable set, we have another integration is called Lebesgue integration, Lebesgue-Stieltje integral. But we are concentrated our all theory in the Borel sigma algebra and Borel set and on the Riemann integration. So this is called Riemann-Stieltje integration. And so again, this is again a measure. So any measurable function, if you have a measurable function and if you integrate that measurable function over another measure, then it's give again a new measure. So like if you measure your length over another length, this is get to the area. If you measure that length with respect to the area, then it will be volume, like in the three-dimensional thing. So in R2. So in Riemann integration theory, you know, this is like a surface. Now if any function like a surface, now f of x y for the zero, that's like a surface, it's like a surface, and you have some area where, and you are going to find that volume. So this gives some surface, corresponding surface. You want to find the volume in this region. This is a region is R. And how do we write? If this function is S, we write the integration f x y dx dy. Sometimes like the double integral, or maybe you can use a single integral. So you can use this double integral. So this is a volume. Now same thing we can do. We can take not only here is the area measure, the dx dy is the area measure. You can take any other in general measure. So you can take just any general function, 2 or 3 dimensional, and you take a different measure. different measure on that. Different, not the area measure. You can take any other measure on the plane. So this is going to be another measure. So there is a now question of the product measure, and I will not discuss on that in this video. We are discussing only the integration as a measure and how to find another measure from a with a measurable function and a measure, and is how we go to the one-dimensional to two-dimensional integration, and from two to three-dimensional integration volume measure. And we have this Borel thing, and same Borel sigma algebra and Borel set can be constructed in R2 and R3 and in general n dimension, and the integration theory can be developed in the n dimension also, as well as the only not only the Riemann integration, this can be generalized the Riemann Stieltje integration also over any measure. So that's all for today's class.